In 1964, Bob Wilson and his colleague Arno Penzias were using the horn antenna to search for natural radio emissions from our own galaxy. But as soon as they switched their giant earpiece on, it started humming. It was picking up weak but constant background interference. Wilson and Penzias had no idea where the signal was coming from. At first, they suspected nearby New York, but when they ruled that out, their suspicions turned on the local bird population.
There were a pair of pigeons living in the antenna. Once a week, we'd come up and disturb them. They'd fly away, but the next day when we were gone, they'd come back. So the inside of the horn was covered with white pigeon droppings. We got up in the horn reflector with a broom and swept it all out.
With the pigeons evicted, the two scientists were disappointed to find the interference was still there.
We looked in various directions. Sometimes we looked at specific objects, other times we looked at random parts of the sky, and every time we did that, we saw the same level, the same amount of excess noise. It was the same in all directions.
They began to realize that it could have a more dramatic origin. What Wilson and Penzias had stumbled across was a background of microwave radiation, a faint afterglow of the battle that defeated antimatter 12 billion years before.
The microwave background comes from the initial very dense and hot stage of the universe. And as the universe expands, the radiation expands with it. And just like anything else that expands, it tends to cool off. It came from the early stages of the universe, and it's just out there. If you go outside, it'll hit you on the head. You won't notice it because it's so weak. It's at such a low level that it's almost undetectable.
Every television set on Earth can detect the radiation from the Big Bang. Antimatter had been defeated, and the universe was still only a second old. Over the next 3 minutes, the explosions created the kind of matter we would recognize today: hydrogen and helium. It was still too early for the universe to shine. In the dark ages that followed the Big Bang, these elements would combine together and provide the building blocks of the first generation of stars and galaxies. The atoms created 12 billion years ago are still with us today. Since the Big Bang, the universe has continued to grow and expand. To understand just how big it has grown, we need to take an imaginary spaceship ride from the Earth to the edge of the visible universe. Our nearest neighbor is the Moon, just 250,000 miles away. At the center of our solar system, 93 million miles away, is our Sun. After crossing the center of our solar system, we continue our flight beyond the orbit of the Earth. The next planet out is Mars. Beyond the orbit of Mars is the asteroid belt. A billion miles away is the giant outer planet Saturn, almost 1,000 times the size of Earth. As we leave the solar system, we would pass one of our earliest interplanetary explorers, Voyager 1, launched in 1977 and traveling at a mere 40,000 miles per hour. Proxima Centauri and Alpha Centauri, A and B, our nearest stars, are 25 million miles away. Our solar system sits in the quiet suburbs of a spiral galaxy, the Milky Way, a star city containing over 100 billion stars. Every star we can see in the night sky lies within our own galaxy. This is deep space. Out beyond the Milky Way, 10 million miles from Earth, is the next spiral galaxy, Andromeda. Even traveling at the speed of light, it would take 2 million years to reach here. Andromeda and the Milky Way form part of a small cluster of galaxies called the Local Group. But stretching out way beyond the Local Group are much greater clusters of galaxies. If it were possible to travel fast enough for long enough and reach the edge of the known universe, this is what we would see. Uneven clusters of galaxies, a pattern that was predetermined in the very first second of the Big Bang. This is as far as our spaceship can take us. We are now 50 billion trillion miles from Earth. This is where science ends and speculation begins. Astronomers may never see what lies beyond here. This is where the secrets of the universe are hidden. For centuries, astronomers have been trying to locate our exact position by looking further and further across the vast expanses of deep space. For 400 years since Galileo first pointed his telescope at the sky, astronomers have not only been looking across the far reaches of space, but back in time. Because the light from distant objects takes so long to reach us, every telescope is a time machine. Even traveling at an unbelievable 186,000 miles per second, light takes a long time to cross space. Light reflected off the surface of the moon is already over a second old by the time it reaches us on Earth. Look up at Saturn, and you're seeing it as it was 1.5 hours ago. And we see Andromeda as it was when the first humans walked the Earth. Its light has been traveling across space for over 2 million years. Here at the Lick Observatory, Sandra Faber spent her early career unraveling the mysteries of the most distant galaxies.
The biggest telescopes on Earth now are taking us back billions of years into the past, 90% of the way back to the beginning of the universe.
View light from the furthest visible galaxies, and you're seeing them as they were over 11 billion years ago.
A galaxy is really like a city of stars. Just as there are billions of people on Earth or millions of people in a city, there are hundreds of billions of stars in a typical galaxy.
The universe contains over 100 billion galaxies. Like giant hurricanes in space, their resident stars spin around a giant central core. To see into the heart of the most distant galaxies would require a very special telescope. In 1990, the launch of the Hubble Space Telescope promised astronomers a view of the early universe they had only dared dream of. High above the Earth's atmosphere, this billion